Hello everyone. Today we cover section 3.6, linear inequalities in two variables. Firstly, what kind of inequality is a linear inequality in two variables? We're going to look at some inequality and then show you a trick to determine if an inequality is a linear inequality in two variables. Let's see the first one. 3x minus y is less than 9. It is an inequality because it contains an inequality symbol. How do we know the inequality is linear inequality in two variables? If we replace the inequality symbol with equal sign, keep everything else in the inequality the same. The left-hand side the same, right? 3x minus y, the right-hand side the same. So simply remove the inequality symbol, replace it with equal sign. If you have a straight line, then the original inequality is linear inequality in two variables. Yeah, that is my trick to see or to identify linear inequality in two variables. So if you switch the inequality symbol, if you change the inequality symbol to equal sign, you got a linear equation in two variables. The whole chapter, we are talking about linear equations in two variables, right? Linear equations in two variables are straight lines in a rectangular coordinate system. So if you remove the inequality symbol and change it to equal sign, if you have a straight line, this is a straight line, right? You tell me 3x minus y equals 9. Is that a straight line? In what form? We have learned three forms for straight lines. Standard form, slope intercept form, or point slope form? Standard form, exactly, yeah. So the original inequality is a linear inequality in two variables. Yeah, this is how do we identify linear inequality in two variables? Let's see another one. Let's see the second inequality. It is 2x plus 5y bigger than or equal to 0. How do you know this inequality is a linear inequality in two variables? How do we know that? What's the trick that I just told you? Yeah, you change the inequality symbol to equal sign, right? Let's see what we have. We have 2x plus 5y equals 0. Is that a straight line? 2x plus 5y equals 0. Is that equation a straight line? Yes or no? Yes. What form? Standard form. Yeah, exactly. So number 2 is also a linear inequality in two variables. Linear inequality in two variables. Number 3, inequality x is bigger than -2. Determine if this inequality is a linear inequality in two variables. Huh? Use the trick. If we use the trick, we change the inequality symbol to equal. We would have an equation, x equals -2. Is x equals -2 a straight line? Does x equals -2 represent a straight line in the rectangular coordinate system? Huh? Yes? What kind of line? What kind of straight line? Oblique, horizontal, vertical? X equals -2. Yeah, it is a straight line. What kind of straight line? You're right, vertical. Yeah, this way, vertical. Exactly. So number 3 is also a linear inequality in two variables. The trick is very useful and convenient to identify linear inequalities in two variables. Number 4, determine if y is less than or equal to 6, a linear inequality in two variables. Yeah, let's use the trick. We change the inequality symbol to equal. And we got a y equal to 6. Does the y equal to 6 represent a straight line in the rectangular coordinate system? Yes? Yeah, what kind of line this time? Horizontal, exactly, perfect. Yeah, so those inequalities, by using the trick, we see all of them are linear inequalities in two variables. The focus of today, the focus of this section is to graph solution set of a linear inequality in two variables. We need to graph the solution set. Yeah. So firstly, I wanna explain the concept of a solution for a linear inequality in two variables. Okay, yeah. So A comma B, if an ordered number pair A comma B satisfy a linear inequality in two variables, then the ordered number pair A comma B is a solution of the linear inequality in two variables. Linear inequality in two variables. That's how do we define a solution for a linear inequality in two variables. Look at our inequality here. 3x minus y is less than 9. I'm going to give you a few ordered number pair. And you help me to determine which of them are solutions, which of them are not solutions. So let's try this one first. And then let's try 1, 5. And then let's try 0, -5. And then let's try 10, -5. Yeah, I just randomly wrote some ordered number pairs. Let's determine. Okay, you guys do that. Number 1, how do we determine if 0, 0 is solution of the linear inequality in two variables? How do we know? By the definition, if 0, 0 satisfies the inequality, it is a solution. Otherwise, if it does not satisfy the inequality, it's not a solution, right? How do we know? How do we know if 0, 0 satisfy or not? Should we plug in? Okay, let's plug in x equals 0, y equals 0 back into the original inequality. The original inequality is 3x minus y is less than 9. We use parentheses to hold the places for x and y. And then we're going to put a 0 in the place of x and y. What is 3 times 0? 0. 0 minus 0 is 0, right? So we got a 0 is less than 9. Tell me please, is 0 is less than 9 a true statement or contradiction? 0 less than 9. True statement, of course. Since after we plug x equals 0, y equals 0 into the inequality, we got a true statement. 0, 0 satisfies the inequality. So 0, 0 is a solution, right? Okay, can you determine the second? Can you try the second, 1, 5? And let me know what you have. This time you're going to plug in x equals 1, y equals 5, right? X equals 1, y equals 5. And let me know what you have. Do you have a true statement or contradiction? Sarah, do you have an answer? Not yet? Okay, take your time. Sammy, what do you have? You plug in x equals 1, y equals 5. Do you have a contradiction or true statement? Angela? Remember, please excuse my de-understanding. You're going to follow the correct order of operations. You have 3 minus 5, right? That's good. 3 minus 5. -2, exactly. You have -2 is less than 9. 3 minus 5 is -2. You have -2 is less than 9. True or false? True. Okay. Means this is also a solution. Right? Okay, number 3. Let's try this time. X equals 0, y equals -5. Okay, we're gonna determine if 0, -5 is solution. We have x equals 0, y equals -5. Yeah, be careful the sign. Y equals -5. And let me know what you have. What is 3 times 0? 0. -5. What's -5? Positive 5, yeah. So we have 5 is less than 9. True or false? True. Okay, we got another solution. Let's see number 4. The ordered number pair is 10, -5. This time we are going to plug in x equals 10, y equals -5. Yeah, please let me know what you have. 3 times 10 minus -5. Minus -5 is the same as plus +5. What do you have? 35. Okay, we got a 35 is less than 9. True or false? False. Okay. Yeah, those are just the random ordered number pairs I gave you. In effect, there are infinitely many, uncountably many ordered number pairs satisfy a given linear inequality variables. Also, there are infinitely many, uncountably many ordered number pairs do not satisfy the any given linear inequality to variables. So the fact is, any given linear inequality to variables has infinitely many solutions. Okay, has infinitely many solutions. Yeah, let me repeat it. The focus of today is to graph the solution set for a given linear inequality to variables, right? The solution set contains all the solutions of the inequality. And any given linear inequality to variables has infinitely many solutions. Yeah, so today we're going to figure out what are the infinitely many solutions for any given linear inequality to variables. So today we are going to graph those 4 examples, okay? Yeah, 1, 2, 3, 4. Today we are going to graph the solution set for those 4 problems. They have different purposes, okay? Yeah, I'll show you there's a purpose for each example. Let's look at the first example. Let me to erase that. Let's see the first inequality. The first inequality is 3x minus y is less than 9. It is a linear inequality in 2 variables. We are going to graph the solution set for this inequality in 2 variables. I have a procedure. I'll show you the procedure. Step 1. Change the inequality symbol. Yeah, this is the time when you should take notes. Symbol. Change the inequality symbol to equal sign to get the boundary line and graph the boundary line. Graph the boundary line. Yeah, let's do one step at a time. Yeah, let's follow the instruction for step 1. Change the inequality symbol in the inequality to equal sign. We have 3x minus y equals 9. Okay? Yeah. So this is the linear inequality to variables. Yeah. So if I remove the inequality symbol, change it to equal sign, I have a straight line. We did this earlier, right? This straight line is the boundary line. Is the boundary line of the solution set of the inequality. It's easy, right? But we have to graph the solution. We have to graph the boundary line. Let's graph it. Let's graph it. Let me draw the system. Rectangular coordinate system. All right. Let's see where is, let's see how do we graph 3x minus y equals 9. How do we graph this boundary line? Tell me what's the form of the equation of the line? Standard form, okay. Do you guys remember if the equation is in the standard form, most of the time it's very convenient for us to find the x-intercept and the y-intercept. Do you guys remember that? If the straight line is in the standard form, most of the time it's very convenient to find the x-intercept and the y-intercept. If we know the x-intercept and the y-intercept for a line, we are able to graph the line. We're going to do the idea, okay? We're going to follow the idea. 3x minus y equals 9. 3x minus y equals 9. Let's see what is the x-intercept. In order to find the x-intercept, how do we do that? We learned this probably last week. Yeah. How do we find the x-intercept? We make y be 0, okay? In order to find the x-intercept, we make y be 0. And we have 3x equals 9. And what is x? 3, right? Yes? So 3 comma 0 is the x-intercept. How do we find the y-intercept? To find the y-intercept, we make x be 0. We make x be 0, we have negative y equals 9, and y equals negative 9. So 0 comma negative 9 is the y-intercept. Let me show you something. It might remind you what we just did earlier. Okay. If the equation is in a standard form like that, like this, in order to find the x-intercept, we make y be 0, right? Make y be 0. Remember that? We did the similar thing the first section of this chapter, right? Make y be 0, so this part disappears. And we have 3x equals 9, right? 3 times of x is 9, so x is 3. It's very convenient, right? So 3 comma 0 is the x-intercept. For finding y-intercept, we make x be 0. So this part disappears. We don't have this part anymore, right? So we have negative y is 9. If the opposite of 9, if the opposite of y is 9, then y is the opposite of 9, which is negative 9. You see that? So 0 comma negative 9 is the y-intercept. We did the same thing before, right? When we learned x-intercept and y-intercept. Yeah, so let me repeat. When we graph a line, there are a few different methods to graph a line. But basically, as long as we can find 2 different points on a line, we are able to graph it, right? Yeah, if the equation of the line is in a standard form, most of the time it's very convenient to find the x-intercept and the y-intercept. Yeah, x-intercept and y-intercept are on the line. They are different, so we are able to graph the line. All right. Let's see, where is the x-intercept 3 comma 0? Where is 3, 0? 1, 2. Let me make them the unit smaller. Say 1, 2, 3. That's 3, 0, right? Where is 0, -9? So that is 3, that's 6, that's 9, -9. So 0, -9. Am I right? Yes or no? Okay. So if I connect the 2 points, we will have the boundary line we are looking for, right? Okay, here. Instead of graphing a solid line, I'm going to graph a dashed line. I'm going to explain why. And I'm going to add something to the first step. Here. If the original inequality symbol is less than or equal to or bigger than or equal to, draw the boundary line. Draw the boundary line solid. Draw the boundary line solid. If the original inequality symbol is strictly less than or strictly bigger than, then draw the boundary line. Draw the boundary line dashed. Sorry, my writing is not the best. It's really hard to write in this position. Okay, make sure you have that sentence in your note. Yeah, that's the first step, complete. The first step, change the inequality symbol in the inequality to equal sign. Then you have a straight line, right? That straight line is going to be the boundary line of the solution set of the inequality. And you're going to graph the line. You're going to graph the line. And if the original inequality symbol is less than or equal to or bigger than or equal to, you graph the boundary line solid. Otherwise, you graph the boundary line dashed. In our case, this is dashed, right? The reason is because the original inequality symbol is strictly less than. The original inequality symbol does not contain the equality, right? You see what I'm talking about? You guys see what I'm talking about? I will explain why it's like that, okay? Please have those steps. Please have the first step written down in your notes. Are you guys ready? Okay. If the original inequality symbol contains the equality, it is less than or equal to or bigger than or equal to, you draw the boundary line solid. Otherwise, you draw the boundary line dashed. Okay, let's see the second step. Let's see the second step. Step 2. Pick a testing point or testing point. Yeah, what is a testing point? Any point that is not on the boundary line can be used as a testing point. Okay. So step two, we are going to pick a testing point. We are going to pick a testing point. What kind of testing point? I always pick 0, 0. As long as 0, 0 is not on the boundary line. In this case, it's 0, 0 on the boundary line. This is the boundary. This is the 0, 0 origin. Is 0, 0 on the boundary? Of course not, right? Obviously not. Okay, so we can use 0, 0. We're gonna plug in plug x equals 0, y equals 0 into, be very careful, into the original inequality, not the equation, okay? Into the original inequality. I think I should have this part in red as well. Yeah, plug in the testing point into the original inequality. If you have a true statement, if you get a true statement, shade the region let me just erase that. Shade the half plane. Yeah, let me word it this way. Shade the half plane containing the testing point. Otherwise, shade the half plane without the testing point. Yeah, please have the sentence written down. And now let's make sense of it, okay? Second step, once we have the boundary line, yeah, let's see the boundary line. Let's look at the rectangular coordinate system. It is a two-dimensional space, right? How many points on it? All over places, right? Infinitely many, uncountably many points. And remember this straight line, forever, 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 this direction, forever, forever. So this straight line cuts or divides the whole plane into half, right? Yeah, the straight line divides the whole plane into half. This half plane above and the half plane below the line, right? Okay, remember the boundary line is the boundary, the straight line is the boundary of the solution set. The straight line is the boundary of the solution set we are looking for. This means the solution set must be either this half plane or this half plane, right? Does that make sense? Okay, which half plane? In order to know which half plane, we need to get a testing point. One method, I only teach one method in the class. I know there are many different other methods. In the class, I only teach one method. In order to know which plane, we pick a testing point. Most of the time, I always use 0, 0 because it's easy, it's convenient. As long as 0, 0 is not on the boundary. In this case, origin is not on the boundary, so we can use 0, 0, right? And I plug in 0, 0. Yeah, let's plug in 0, 0 into the original inequality. The original inequality is 3x minus y less than 9. 3x minus y is less than 9, right? Let's plug in 0, 0. Plug in x equals 0, y equals 0. And what do we have? Do we have the 0 is less than 9? Do you have a true statement or contradiction? True statement, right? Yeah. We have a true statement means 0, 0 is a solution of the inequality. Does that make sense? So the testing point, the black testing point, is a solution of the solution set we are looking for. Yeah, by the guideline, by the step 2, we are I wrote, then we are going to shade the region, shade the half plane containing the testing point. So this region is not possible for me to shade all the region, okay? Just to show you all the points, the region, the whole half plane above the boundary line. Yeah, all the points in that region, in the shaded region, they are solutions of the inequality. Together, this region is the solution set of the inequality. Does that make sense? Am I clear? Yeah, let me explain why. We choose 0, 0 as the testing point, right? Turns out 0, 0 is a solution. Means this point, this black point, is in the solution set or in the region we are looking for. So we shade a half plane above the boundary line, which contains the origin, which is the solution. Otherwise, if we shade the region below, then we will see a contradiction, right? Because the origin is a solution, but it's not in the solution set. That's a contradiction. Does that make sense? You guys have the second step written down. Take your time. Step 2, you pick a testing point. Most of the time I use 0, 0, as long as 0, 0 is not on the boundary line. Plug in the testing point into the original inequality. If you got a true statement, means the testing point is a solution, then you shade the half plane containing the testing point. Otherwise, you shade the half plane without the testing point. And that's how do we graph the solution set for a given linear inequality in 2 variables. Does that help? Yes? Any questions? Yeah, make sure you have this sentence, you have the second step written down. Those are just in my words, okay? You can understand it well and word it in your own words, write it in your own words. Yeah. Let me know when you finish. Okay, now let me explain why, in this case, the first example, why would we draw the boundary line a dashed straight line? Why is it not a solid? It is dashed. We draw the boundary line dashed to display the fact the points on the boundary are not solutions. Okay? Do you see what I'm talking about? Yeah. We draw the boundary line dashed to display the fact that the points on the boundary do not belong to the solution set. They are not, because the inequality is strictly less than. The points on the straight line do not belong to the inequality, do not belong to the solution set of the inequality. Does that make sense? Yeah. So as long as you follow the 2 steps, you can always graph the correct solution set for the given linear inequality 2 variables. In the test, you know all my problems are multiple choice questions, right? So you just need to choose the correct graph. You would have A, B, C, D. You just need to choose which one has the correct boundary line and the correct region. Then you choose the one satisfy that. Okay, the second problem, I want you to work with me together. And you're going to guide me for the second problem. You have the 2 steps written down in your note, right? So the second inequality, you're going to tell me what to do. It is 2x plus 5y. 2x plus 5y. 2x plus 5y. bigger than or equal to 0. All right. We are going to graph the solution set of this inequality. You tell me what to do. You tell me what to do. What should I do? Yeah, change the inequality symbol to equal sign. And we have a straight line, right? And this is the boundary line. This is the boundary line of the solution set of the inequality. And now what should we do? What should we do? Huh? Graph it. You're right. Yeah, let's graph it. Let's get a rectangular coordinate system. All right. How do we graph it? How do we graph it? How do we graph 2x plus 5y equals 0? What kind of form? What form this equation is in? Yes, the form. Okay. So how do we graph it? Plug in 0 for what? Okay, then let's plug in x equals 0. What do we have for y? Yeah, 0. So this equation, this straight line, passes the origin. Yeah, when you try to find the intercept for this equation, you notice this equation has an x-intercept and a y-intercept both equal to 0, 0. Yeah, obviously, if you make y be 0, you make y be 0, 2x is 0, so x is 0, right? If you make x be 0, 2y equals 0, y equals 0. So both x-intercept and y-intercept is 0, 0. Well, okay, at least we have one point right now. But we need two different points in order to graph the line. How do we find the other point? How do we find the other point? Plug in, we did that already. Yeah, that's a good idea. You can actually find any point on the line, right? You can randomly just find a convenient ordered number pair satisfy the equation. How about, let me look at it. How about let's make y be -2. If we let y be -2, let's see what happened. Then 2x plus 5 times -2 equals 0, right? Yeah, I plug in y equals -2 in the equation. What is 5 times -2? Positive times negative? Yeah, -10, right? -10 equals 0. Could we move the -10 over to the right-hand side, become +10? Yes? Could I? Yeah, transposition, right? We move -10 over to the right, so negative becomes positive. And divide both sides by 2, what do we have for x? 5. Correct? 10 divided by 2 is 5, right? What does that mean? Means 5 comma -2 is a solution, or is on the line. Is on the line. And you might wonder, why did you make a y equals -2? How do I know I should make a y equals -2? You don't have to. You can make a y maybe be another number. Yeah, I just think at least I don't want fractions with decimals, right? So if I plug in y equals -2, I would have x equals a whole number. Yeah, I just randomly get this solution. You can try other order number pairs, okay? Yeah. Where is the 2? Where is the 5 comma -2? Which quadrant? 2, 3, 4, 5. Yeah, quadrant 4, exactly. Right here, right? All right, I'm going to connect the 2 points to graph the boundary line. Hold on. Should I graph the boundary line dashed or solid? Look at your note. If I connect them, I would have the boundary. Should I? How do I graph the boundary line. Solid or dashed? Solid or dashed? Yeah, solid, right? Is bigger than or equal to. The original inequality symbol has an equality in it. So we need to graph the line dashed. I'm sorry, solid. Graph the line solid, okay? That's the boundary line. Is the boundary line solid? Let me explain the original inequality. The original inequality actually means 2x plus 5y bigger than 0 or 2x plus 5y equals to 0. This part means all the points on the boundary belong to the solution set, right? Yeah, let's start. So bigger than or equal to. Bigger than or equal to means bigger than, strictly bigger than or equal to. This case, all the points on the boundary line, they are solutions of the inequality. So that's the reason we graph the boundary line solid to display a fact. What fact? All the points on the boundary, they are solutions. All right, that's the first step. Can you guide me through the second step? What should we do? This boundary divided the whole plane into half, right? Half plane above, half plane below. And which half plane is the solution set? How do we know that? How do we know that? What's the second step? Testing point, okay. Would a 0, 0 still work? We need a testing point, right? Would a 0, 0 still work? Could we still use 0, 0 to be the testing point? No, remember I wrote in the step 2. We need a testing point. It could be any point as long as it's not on the boundary line. 0, 0 is convenient. However, in this case, we cannot use it because 0, 0 is on the boundary, right? Then what should we do? What should we do? Any point would be okay. Yeah. All those points above or all those points below. Of course, we don't want to choose we do not want to choose a testing point with coordinates, decimals, or fractions, right? Yeah, we want to make our job easier. So we want to choose the testing point as convenient as possible. How about 1, 1? Yeah, I just randomly choose 1, 1 because 1 is easy, right? All right. So please help me to plug in x equals 1, y equals 1 into where? We plug in into the equation or original inequality. Look at your note. Yeah, please look at your note. Plug in where? Plug in the testing point into where? Yeah, original inequality. This actually is a common mistake. They plug in on the straight line. The original inequality, okay? So it's 2x plus 5y bigger than or equal to 0. Yeah, we're going to plug in here. X is 1, y is 1. What is 2 times 1? 2. What is 5 times 1? 5. So we have a 7 is bigger than or equal to 0. Is a true statement or a contradiction? True statement, okay. True statement means 1, 1. The testing point is a solution, right? Okay, you tell me. Let me graph where is the testing point. This is the testing point. The black point 1, 1 is the testing point. So should we shade the region above or shade the region below? Should we shade the region above the boundary line or the region below the boundary line? Above. Do you guys agree? Yeah, because the testing point is above, right? So you shade the region above. Yeah, of course, I could only shade a part of the region. You're gonna know the rectangular coordinate system has no boundary, has no bound from all the directions. So the half plane has no bound above the straight line, above the boundary line. So all the points above the boundary line, including the points on the boundary line, they are solution set. They are solutions of the inequality. Does that make sense? There's a reason for this example. In this example, the boundary line happened to pass through the origin. So if the boundary line passes through the origin, we can't use 0, 0 be the testing point anymore. We have to use a different point to be the testing point, right? Okay, so that's the reason. That's the reason. Number 3. Any question about number 2? Then let's see number 3. What's number 3? X is bigger than -2. X is bigger than -2. We need to graph the linear inequality in 2 variables, which is x is bigger than -2. Okay, 2 steps. You guide me. What should we do? What should we do? Yeah, change the inequality symbol to equal sign, right? And we should have a straight line. You know that is straight line. That line is the boundary line of the solution set of the inequality. Okay. And what should we do, Ian? What should we do here? We found the equation for the boundary line. Graph it. Okay. Can you help us to graph it? What kind of straight line that is? Slant, horizontal, vertical. X equals -2. Yeah, what kind of straight line that is? Vertical, yeah, x equals -2, right? So 2 units to the left of the origin. And we graph a vertical line. Hold on, should we graph the vertical line, the boundary line, solid or dashed? Solid or dashed? Huh? Dashed, right? Exactly. We need to graph it as dashed. Do you see the reason though? Because the inequality symbol is strictly bigger than, right? Yes? So this is -2, 0. Yeah. So this is the boundary line, right? It's a dashed vertical straight line. Okay, that's the first step. What's the second step? Testing point. Okay, what's the testing point? Yeah, 0, 0. Please always use 0, 0. As long as 0, 0 is not on the boundary. Okay, let's plug in. X equals 0, y equals 0 into the original inequality. What's the original inequality? X is bigger than -2, right? Yeah, let's plug in. X equals 0, so we have 0 is bigger than -2. Is a true statement or contradiction? True statement. Yeah, for some reason, all the 3, bless you, so far all the examples, the testing point are always a solution, right? There are cases the testing point might not be solution. We'll see if number 4 is that case. In this case, the testing point is a solution. So should we shade the region to the right or shade the region to the left of the boundary? To the right, right? Yeah, the vertical boundary line divided the whole plane into 2 parts. Half plane to the right, half plane to the left. And in this case, we have the solution set half plane to the right because the testing point is to the right of the boundary, right? Yeah. So all the region, all the points to the right of the boundary vertical straight line are solutions of the inequality. Is that clear? Yeah, why do I have this problem? Because the boundary line is a vertical line. The boundary is a vertical line. The previous 2 examples, the boundary are oblique straight line, right? This case is a vertical. There's a reason those examples Those are good examples, so I hope you can practice them a few times after. Number 4, let me see example number 4. The inequality is y no more than 6. Y is less than or equal to 6. Okay, you guide me through. Look at the 2 steps in your note. You tell me what to do. What should I do? Yeah, change it to equal sign, and we got a straight line, right? Is the boundary line. Okay, then what should we do now? We're gonna graph it. Yeah, we're gonna graph it. Graph it. How do we graph y equals 6? What kind of straight line that is? So yeah, it's gonna be a solid boundary line. So how do we graph it? Horizontal, you are right. Very good. Good job. 1, 2, 3, 4, 5, 6. Yeah. We're gonna draw a horizontal line 6 units above the origin. And a solid. You are right, Saria. Is a solid line because the original inequality symbol is less than or equal to has equality in it. Okay, yeah. So that means all the points on the straight line, on the boundary line, also solutions of inequality. All right, second step. What do we do? Testing point? Yeah. I would use 0, 0, right? Because it's very convenient. So let's plug in. X equals 0, y equals 0 into the original inequality, which is y is less than or equal to 6. Plug in y equals 0, you have 0 is no more than 6. Is that a true statement or contradiction? True. Yeah, for some reason, all the 4 examples, the testing point happen to be our solutions. There are cases the testing point might not be solutions. Yeah, so when you work on your homework in MATLAB Math, you might see something like that. Just follow the instruction. If the testing point is not a solution, you just shade the region, the half plane, without the testing point. It happens those 4 are all solutions. So we're gonna shade the region what? Above or below? Below, right? Yeah, below, yeah. Because the testing point is a solution, right? Yeah, 0, oops. The region cannot go beyond the boundary line. All the points below or on the horizontal boundary line. And those points are all solutions of the inequality to variables. Okay? Does that make sense? Yeah. There's a reason for this example. You might already see it because the boundary line is horizontal. So let's make a summary. We have those 4 examples. The first example is a regular example. Boundary line is a slant, does not pass through origin. Second example, boundary line is slant but passes through origin. So you would have to find a different point to be the testing point. Number 3, boundary line is vertical. Number 4, boundary line is horizontal. All right. So I would recommend you practice those 4 examples a few more times to grasp the 2 steps. Because when you take the test, it is closed book, closed note. You would not have the note with you. So you want to remember the procedure. Any question about this section 3.6? Any questions? Then let's move to section 3.7. Introduction to functions. Introductions to functions. Please, firstly, write down the first definition. Relation. 3.7. We start from the definition of relation. Please write down the definition for relation. A relation is a set of ordered pairs. It's a pretty simple definition. It's a pretty simple definition. A relation has domain and range. Please also copy down the definition of domain and range of a relation. Domain of a relation is a set containing all the first components of the ordered pairs in a relation. Range is a set containing all the second components in the ordered pairs in the relation. Please have those definitions on your note. Relation, what is a relation? Domain of a relation, range of a relation. You're going to use those three definitions all the time, okay? In this section. And let me know when you finish the copy. You finished? Okay. No? Okay, sorry. A relation is a set of ordered pairs. The definition is very abstract. It's a very abstract concept. After today, in reality, in real life, you might notice many relations. You might be able to identify relations. Are you ready? Lauren, did you finish? Okay. Okay. So let's look at a few examples and we determine is the given example can be defined as a relation. If it is a relation, how do we find the domain and range for the relation? The first example is a table here. First example is a table, two-column table. The first column gives us a few names, Andy, Bonnie, Cindy, Danny. The second column has the corresponding eye color for those people. Yeah, Andy's eye color is blue, Bobby's eye color is black, Cindy's eye color is brown, Danny's eye color is green. Yeah, that's what we have in this table. I want you to look at the information in the table and determine is the information in the table a relation? Yeah, do you see a relation in the table? Do you see a relation in the table? Yeah, what is a relation? You just wrote down the definition. Anything which can be written in a set, yeah, which can be written as a set of what? A set of ordered pairs is a relation. Very abstract. Anything which can be written as a set of ordered pairs. Yeah, what is a ordered pair? Yeah, I should explain this part. What is a ordered pairs? A pair of gloves, a pair of socks. You know, means it has two pieces, right? Two components, yeah. So in algebra, word lone pair is written as a, we use the parentheses to represent unworded pairs. And the first component, we write the first component and the second component. Here I write the first component as x, the second component as y. And I use the comma to separate the two components and use the parentheses to frame them. In algebra, we use this notation to represent unworded pairs. Before the comma, that's the first component. After the comma, behind the comma, that's the second component. And the order of the two components matters. You cannot randomly switch the order of the two components. Okay, so this is unworded pairs. In anything, if the thing can be written as a set of worded pairs, then the thing is a relation. So now look at the table. Do you see a relation from the table? Do you see a set contains a few worded pairs? Do you see pairs? I would say this is a pair. First component Andy, second component blue, right? Yeah, the person's name and his eye color can make a pair, right? You see that, Sandy? Yeah. Same with Bobby and black. Sandy brown is another pair. Danny and green is another pair, right? We are able to write the information in the table as a set of worded pairs. We are able to write the information in the table as a set of worded pairs. We have 4 pairs, 4 worded pairs in the set. The first pair corresponds to the information of Andy, Andy's name, and his eye color, right? And following the other 3. Do you see that? Yeah, that's how we write the information in the table as a set of worded pairs. By the definition, the table does give us a relation. Does that make sense? Yes? Do you see that? Yeah, anything is very abstract. It's pretty abstract. Anything, if we can write it as a set of worded pairs, that is a relation. Okay, since we agree that's a relation, let's see, how do we find a domain and range for the relation? What's the definition for domain and range in your note? Domain is a set, right? Yeah. Both domain and range are set. Domain is a set. It's set of what? Containing all the domain corresponds to the first component, right? Yeah. Contains all the first component of the pairs in the relation. Okay. What's the first component of the first pair? What's the first component of the second pair? First component. So the domain actually is column 1. Do you see that? Do you see the domain actually is column 1? Yeah. So domain actually is a set. In this case, is a set containing those people's names: Andy, Bobby, Sandy, Danny. Yeah, A, B, C, D. What about range? By the definition, range is a set containing all the second components in the worded pairs in a relation. Yeah, let's see the second pairs in the relation. Blue, black, brown, greens. So the range actually is column 2 in the table, right? Yeah. We can write range as blue, black, brown, green. Here we go. Yeah, so that's the relation in this example, and the relations domain and range. Any questions? Any questions? Now here, I'm going to describe this relation in a different way. I hope you pay attention. We can describe or see this relation as a machine. Yeah, I'm going to describe the relation as a machine. try to make sense of it. I can say we have a machine here. What kind of machine? If you give the machine an input, the machine would produce one or more corresponding outputs. It would produce output or outputs for the given input. And let's see what kind of machine this can be seen as. If I give the machine the name of the person, the machine would produce the eye color for the person. Would that be cool? Kind of a machine, right? If you type in, you put in the name of a person, the machine would tell you what's the eye color for that person. Would that be, it's kind of a program, right? Yeah. So if we give the machine input Andy, the corresponding output would be blue, right? You see that? Yes or no? No? Yes? Kind of relation can be seen as a machine. You give the machine an input, the machine can give you a corresponding output or puts. So for this case, let's see what kind of machine this is. The machine does this job. When you give the machine Andy, if you type in Andy's name, the machine tell you blue. The eye color is blue, right? If you tell the machine, I want to know Bobby's eye color, the machine tell you Bobby's eye color is black, right? If you give the machine Cindy, you type in Cindy's name, the machine tells you Cindy's eye color is brown. If you type in Danny's name, the machine tell you it's green. You see that? Do you see we can describe the relation here as a machine? Yes? Yeah, the inputs are the names of the people. Outputs are their eye colors. Does that make sense? It's very important. Okay. Yeah, we are practicing, we are reinforcing our understanding about relation. So let's do second problem. Let's see the second problem. Second problem. I should have those, erased. What do we have in the second example? In the second example, we have correspondences. In this circle, we have three items. 1, -2, -1. In this circle, we have three items. 2, 3, 6. And from this circle to the other circle, the second circle, we have 4 correspondences. I can color them differently. You can see the blue arrow from 1 to 2, right? The correspondence from 1 to 2. The green arrow from 1 to 3. The orange one from -2 to 3. The purple one from -1 to 6. So we have 4 arrowheads or 4 correspondences in the diagram. You need to determine, do you see a relation? Do you see a relation in the diagram? We are looking at here, okay? We are looking at here. Determine, do you see a relation in the diagram, from the diagram? What is the relation? Yeah, anything that can be seen as a set of ordered pairs. A set of ordered pairs. Anything which can be written as a set of ordered pairs. Do we have some pairs? Look at the blue. It is how do you say that? The initial point is 1, right? Terminal point is 2. Okay, so the arrows go from 1 to 2. 1 and 2 would be a pair, right? And the green one, initial point is 1, terminal is 3. So from 1 to 3, that's another pair, right? The orange is from -2 to 3, -2, 3. Third pair. The purple one is -1, 6. Okay, guys. Do you see the correspondences in the diagram make a relation? The relation is a set containing 4 ordered pairs. 1, 2, that's the blue. 1, 3, that's the green. 2, 3, that's the orange. 1, 6 is the purple, right? You see that? You tell me, what's the domain and range this time? Anyone can tell me what's the domain and range this time? 1, 1, 2, 1. Okay. If we have repeated elements, we only write it once. You're right, we do have 2 twos. Sorry, we do have 2 ones, but one repeated itself twice, so we only write it once. If you have 2 identical elements in a set, you only write it once, okay? What about the range? 2, 3, 6, good. 3 elements, right? Yeah. So turns out, the bubble or circle on the left, that's the domain. The bubble on the right, that's the range, right? So the correspondences go from the domain to the range. Okay. Let's see if we can also describe this relation as a machine. Okay, let's see if we can also describe that relation as a machine. What kind of machine this is? What's the input, what's the output? What's the input, what's the output? What's the input and output? Yeah, so if you give the machine 1, the machine produce what? 2, also what? If the input is 1, it actually has 2 different outputs, right? You see that? Yeah. So if you give the machine input -2, the output is 3. Correct? If you give the machine input -1, the corresponding output is 6, right? Yeah, let's look at this machine. This machine in example 2 has 3 domain elements or 3 inputs. For the first input, the machine gives the input 2 different outputs, right? For the second input, the machine only has 1 corresponding output. For the third input, 1, it also produces only 1 corresponding output, right? And that's the machine. Does that make sense? Okay, very good. This one is very special. It's different from earlier. I mean, not special. I mean, this one is different from earlier. Because for the domain element or the input 1, the machine gives the 1 2 different outputs. It's different from earlier. The first example, for every input, the machine only can produce 1 output, right? Every person only has 1 eye color. Normally, generally. Yeah. So that's the machine for example 2. Let's see example 3. I would ask you to copy down example 3 and consider, is the graph in a rectangular coordinate system? What kind of graph in number 3? 5 points. We have 5 points. 1, 2, 3, 4, 5. Yeah, that's the graph. Determine, is that graph a relation? If it is a relation, what's the domain, what's the range? And what kind of machine this relation is? Okay, I would leave this for you to consider. and we will look at it together tomorrow. Thank you guys for coming. I'll see you tomorrow.